got his bachelor's degree from the University of Western Ontario and his master's degree from Queen's University in Kingston. And then he obtained a PhD in astronomy from the University of Massachusetts. And his first postdoctorate job was at Queen's University, and then he went down to the Jet Propulsion Laboratory in Pasadena. He was at the Dominion Radio Astrophysical Observatory in Penticton for 3 years, and then with the James Clerk Maxwell Telescope in Hawaii, and then for the last 11 years, he's been at Victoria. And he is kind of the person who is the Canadian lead in an incredible epic telescope called ALMA, and I won't spill any more beans and let Gerald give a talk on that. So we'll hook you up here. All right. You just do your talk.
Sorry for the rustle. Probably won't need me using this. I'm in the chorus for Pacific Opera, so I'm used to being able to try to sing so that people at the back of the Royal Theatre can hear me. But I'll use it anyway. I also promised that I wouldn't go off on too many tangents. I'm going to break my promise already. Vera Rubin, I don't know Vera Rubin personally, but her daughter Judy was one of my professors at UMass. And Judy's daughter, Laura, was in my late wife's daycare. So I helped to raise her for her first 3 or 4 years of life. So I got another. As you'll find out, a lot of the things I'm going to tell you about, I have very indirect involvement with, and this is one more of them. I'm very indirectly knowing Vera Rubin. So, going on, let's talk about ALMA and the Event Horizon Telescope. But let's start. I'm going to insult your intelligence by asking you, what is it that you like to look at? You're in an astronomy club. You like looking at stars. Well, what is it about stars that allows you to be able to see them? They give off light. Why? Why do they give off light? Why do they give off light that you can see? Sorry?
Jittery electrons.
Oh, that's getting too technical. They're hot. They're hot. That's exactly it. They are hot. And because they are hot, they give off lots of light that you can see with your eyes. Let's do a little experiment. Come on. Oh, yeah, okay. Telescopes. Lots of telescopes. We like to look through telescopes. There's, oops, I think the pen is gone.
Sorry.
Oh, that's okay.
Trust you.
Yeah, I don't blame you. Let's just go on. Come on. I added special effects. I should not have done that.
What the warps?
There we go. Okay. So, hot things. For instance, the top of your stove. You have an electric stove. You turn the electricity on. Electrons run through the element. It makes the element very, very hot. It starts glowing and gives off visible light that you can see. Well, what happens if you turn the electricity off? It starts to cool down. It cools down enough so that it doesn't give off visible light anymore. But it is giving off some sort of electromagnetic radiation. What is it giving off? Infrared. And you have very good infrared detectors built into you because you can feel infrared. Don't put your hand on there because you will feel it a lot. Your skin is actually a pretty good detector of infrared. Now, so things that are very hot give off visible light. Things that are very warm give off infrared. But what if you took that that stove top and you stuck it into a vat full of liquid nitrogen. Now it's cold. It's really cold. It's not giving off visible light. It's giving off hardly any infrared at all. But it's still giving off some form of electromagnetic radiation. But now it's not nice short waves like light or medium length light waves like infrared. These are very long light waves of order a millimeter, a few millimeters in wavelength, or even less than a millimeter in wavelength. And so if you want to detect something which is very cold, you need to have a detector that can pick up those kinds of electromagnetic waves. They look a lot like radio telescopes. This is the James Clerk Maxwell Telescope. Canada, until the last 3 or 4, when was it? Was it 4 years ago now? Canada was a partner in the James Clerk Maxwell Telescope. I was working there for about 13 years during the real heyday of the observatory. But this telescope is designed to detect millimeter and submillimeter wavelength radiation from space of very, very cold objects. Now, you can't just build a millimeter, submillimeter telescope here in Victoria. And there's a very good reason for that. Does anybody know how a microwave oven works?
Jittery water molecules.
Yes, exactly. What happens is you beam the microwaves into the little cabinet inside a microwave, and the water molecules absorb these microwaves, and it makes them start to spin. And as they spin, because there's a lot of them, they bump into each other, and it causes them to move around faster, and that is the definition of temperature. So by beaming the microwaves into the water, it makes the temperature of the water go up. And so that's how you cook your food or heat your water inside a microwave. Well, there's water vapor in our atmosphere. There's quite a lot of it, especially if you live around here. And so any kind of microwaves, these millimeter, submillimeter waves coming in from outer space are going to get absorbed by that water, the water vapor in the atmosphere, and it's going to make the water vapor start jostling around. But the end result is that those microwaves, those millimeter waves, won't get to the ground. So if you want to detect them, you have to build these telescopes where there's very little water vapor. For instance, at the top of very tall mountains, like this one in Hawaii. This is Mauna Kea in Hawaii. It's also a wonderful place to build optical telescopes. You know that one, Canada, France, Hawaii telescope. There are telescopes that detect optical light over here. There are a couple of telescopes over here that specialize in the infrared. And way over here are telescopes which are specialized for detecting millimeter, submillimeter wavelengths. One of the observatories is over here. This was an early picture before they built the submillimeter array. But over here is the James Clerk Maxwell Telescope. Right down here is a telescope that looks sort of like a football helmet. That's the Caltech Submillimeter Observatory. And knock on wood, they still managed to build a 30-meter telescope. That's going to be down here, down this slope a little piece. But Mauna Kea is a wonderful place to build telescopes because it's above most of the water vapor. It's something like less than 5%, maybe 1% of the sea level water vapor is above you if you are here up at Mauna Kea. Another place to build telescopes would be in Chile. Chile has a plateau. The Atacama Plateau is up at about 5,000 meters. It is extremely dry down there. But I'll get into that later because when I start talking about the ALMA Observatory. Right now I want to look just at the JCMT over here, James Clerk Maxwell Telescope. For a long, long time, for many years, this was the largest telescope of its kind in the world, the largest telescope to detect millimeter and submillimeter wavelengths in the world. And Canada had a significant part of that. And here I am in the control room, looking very tired and very bored because there are a lot of other people who are working. This is kind of a neat project. This was a few years ago. Does anybody remember a space probe called Deep Impact?
Yeah.
It was basically it was a big copper bullet that was going to fly into a comet and smash into it and hopefully create a big crater and scatter a whole bunch of stuff out so that they could, from the Earth, they'd be able to detect the cloud of dust and ice that had been blown out by this bullet, and we'd be able to figure out what this comet was made out of and how it was composed. We were observing it too at the JCMT. They detected it at UCURT, but not JCMT. Okay, great. We have a telescope that detects microwaves and millimeter waves and submillimeter waves from stuff in space. So what? What is it good for? Well, atoms, single atoms. The only thing that an atom can do is have the electrons move up and move in and out. The problem is that when these electrons change the orbit around the nucleus, they have a very, very high energy. So that single atoms only radiate in, say, optical and infrared wavelengths. But if you start getting molecules, the molecules look like little dumbbells. And they not only can they have the electrons spinning on them, but the whole molecule itself can start spinning. But because of quantum mechanics, they can only spin at extremely particular speeds. So if they absorb any energy, they will go from spinning at one rate up to a spinning about twice as fast, or 3 times as fast, or 4 times as fast. And so, and then the speed that they spin depends completely on how heavy the atoms are in the molecule. If you get complex molecules with lots of atoms sticking out in different ways, then they can rotate in a lot of different ways, and you can get all kinds of different kinds of wavelengths of light coming from these molecules. But the speed that these molecules spin is in the frequency that these things spin is of the order of 100 gigahertz or so. A few hundred gigahertz, a few tens of gigahertz. And if you can convert that in your head, that converts into a wavelength of about a millimeter down to a few tenths of a millimeter out to a few millimeters. So molecules can absorb light or absorb radiation at millimeter, submillimeter wavelengths. And the same thing happens if they are spinning fast and they suddenly slow down, they're going to give off radiation at millimeter or submillimeter wavelengths. So using a telescope like the JCMT, we can measure and know exactly, by tuning the frequency that the telescope is detecting, you can know exactly what it is that you're looking at. You can not only can you map where the material is in the sky, but you can detect, you can know that if you tune to exactly 115 gigahertz, that's about 3 millimeter wavelength, that you are detecting carbon monoxide, which is a really common gas in space. So you can find out what you are looking at, what the material is in this area. You know where the material is. You know how much of it there is. You know what it's made out of. Because of Doppler effects. Everybody in this room must know what the Doppler effect is. Anybody know what that is? Okay, good. Well, using the Doppler effect, you can measure how fast the material is moving, whether it's moving toward you or away from you, or how fast it is. You can use these molecules to measure the temperature of the gas that you're looking at, and you can even use them to measure the chemistry by finding what range of molecules are in these clouds. Just for interest, this is a list of a few of the very smelly molecules that have been detected in the interstellar medium. Most of these are carbon-based and with all kinds of strange radicals on them, which on Earth would make them extremely smelly, some of them quite poisonous. Well, that's fine. What actually can we do with it? Well, one nifty little project that I was involved in, one neat thing about working at an observatory and being a support scientist at an observatory, is that I got to support a lot of scientists coming in doing research that I would never have gotten involved in otherwise. This group came in and they were observing the atmosphere of Mars and Venus. And because I was helping them a lot, they actually got me involved in the project. This particular project was to study the atmosphere of Mars. And in particular, what they wanted to do was to measure the temperature and density profile of the Martian atmosphere. This was an advance of the Mars Observer satellite, or the Mars Observer program, which sent a probe in orbit around Mars. But to save fuel, they were going to send it. They were going to send it through the atmosphere of Mars to get the atmosphere to slow the probe down enough for it to go in orbit around Mars, and thereby save a lot of fuel and be a lot and use that weight for more payload. Well, to do that, they needed to know precisely how thick the atmosphere was, and what temperature it was, and how high it was. And so that's what this project was designed for. But while we were doing it, we happened to detect this other spectral line that they weren't expecting. And they realized later that they were looking at they were looking at hydrogen peroxide, H2O2. So we were the first ones ever to detect hydrogen peroxide on Mars, which was kind of fun. And I thought, okay, well, when you publish the paper, what you need to do is the title should be, "Are there blondes on Mars?" For some reason I don't know, it's just boring. They decided not to do that. Some of the other neat things that JCMT was involved in is that the fact that when you look up in the sky, you can see all kinds of stars, but you have seen the Milky Way, but you also have noticed these dark patches in between the stars within the Milky Way. Those dark patches, of course, are not holes. They are clouds of gas and dust. And these clouds of gas and dust are very cold. They're of order a few tens of degrees above absolute zero. They're too cold to give any visible light, and there's too much dust and stuff in them to let visible light even pass through them. They are thin enough that infrared can sometimes pass through them, but they're too cold to give off infrared light. So using a telescope like JCMT, you can map directly the cold gas and dust in which new stars are being formed. So I don't have to tell you what this is. That's why we don't give this to you.
Oh my God.
It's a lot fainter now. But let me particularly look at this. You've all seen it in telescopes, binoculars. It's the Great Nebula in Orion, of course. And what you are seeing is the result of star formation inside the Orion molecular cloud. Most of the stars that are being formed in this cloud at this moment are invisible. You cannot see them, except for a few. And the ones most spectacular ones in particular are these four stars here. They're very, very hot O-type stars, extremely hot young stars. that are heating up the gas in this cloud, and they've blown out this big bubble. And the edges of this bubble have been heated up so that the gas is now glowing, and that's where you're seeing, when you look at it through a telescope, what you're seeing is this glowing gas. Plus, you probably will see these four stars in the trapezium that are the O-type stars. Up here, these are young hot stars, but they're not. They're what you're seeing here is light reflected off the dust mostly. Well, with an infrared telescope, and again, infrared telescopes need to be built way up high on top of mountains or put into space. This image was made with the Spitzer Space Telescope. Using an infrared telescope, you can now see in this area where there are hundreds, literally hundreds of young stars that are in the process of being born. What you're seeing here is the glow of the dust around these young stars as the dust is falling into the star and forming the new star. But using the JCMT or millimeter telescope, here we can map the dust and the gas itself out of which these stars are forming. And using maps like this, we can start to understand how you go from a big pile of gas to forming a star. It's still a very active research field, but the JCMT made a big contribution to that. Another contribution that the JCMT was involved in was looking at nearby stars. An interesting discovery was finding that there's a lot of dust around a lot of nearby stars. They're called debris disks. So this is the Epsilon Eridani star. It's only it's one of the closest stars to us. It's a fairly young star, not nearly young enough to be called a star-forming region, but this is still only a few 100 million years old. But it is this star was found to have a huge disk of dust around it. And this is sort of an artist's impression of what this dust is from. But the star is too old to have dust like this. So the JCMT was instrumental in discovering that a lot of these stars have a huge reservoir of dust that shouldn't be there. Because there's wind coming off from the star, the light from the star itself, we should be blowing this dust away. The dust should be gone. It shouldn't be there. So something is causing the dust to be regenerated. How? Probably comets. By knowing how much dust is around this star, and knowing how long the dust can last, we figure that this star, Epsilon Eridani, must have something like 1 to 10,000 times as many comets as our own solar system does. And the comets are so common that they are as they're falling in, they're evaporating, but they're also colliding with each other, creating this huge ring of dust. Another thing the JCMT was very much involved in, it was a big discovery, was mapping galaxy fields. This is the Hubble Ultra Deep Field. I'm sure that you've seen it before. I don't know if any of the spots that you see are nearby stars. As far as I know, pretty well everything that you see in this image is a galaxy, a faraway galaxy. Well, the JCMT was used to map regions like this, and it discovered a whole new class of galaxies that are simply invisible at the optical. They are not seen in the optical, but they have they are pouring out so much energy just in the millimeter, submillimeter wavelength, that they realize that these things must be forming hundreds and hundreds of stars every year. The realization is that we are looking at the period of formation of most stars in the galaxy through the study of these submillimeter galaxies. Now, this image right here tells you why I don't do cosmology, because it's about the most boring picture you can imagine. Well, great. JCMT has been involved in some incredible discoveries, just absolutely phenomenal discoveries. So, are we done? No, of course not. I don't have to tell this group about Aperture and
Bigger is always better.
Bigger is always better. Why? Why is bigger better?
No, with you guys, it's resolution.
That's number two. What you want is sensitivity and aperture. Sensitivity and resolution. Sensitivity, you get a bigger mirror, you collect more light, you can see things that are a lot fainter. But at the same time, if you make your telescope bigger, you can also see things in finer detail. That's not quite so true in optical astronomy. I mean, you have, especially at the level of telescope that people have here. I know people here have some phenomenal telescopes, but you get a 6-inch telescope versus a 20-inch telescope that you can see a lot fainter things with the 20-inch telescope, but you're not going to see things much better resolution just because the sky, because of seeing, the atmosphere distorts things. But if you took your telescopes out of the atmosphere, so you didn't have that jitter all the time, then the resolution that you can see things goes as 1 over the diameter. So if your telescope is twice as big, you can see things that are only half the size. What does that mean? Well, little telescope maps the sky. Hey, we found blobs. And for the most part, using the JCMT, I have heard it described as blob science. Very exciting. But if we build the telescope bigger, wait a minute, there's some structure in those blobs. But you know what? I want to be able to figure out, what are those blobs? What are they doing? Let's build a really big telescope. And now, hey, there's a lot of interesting stuff in there. But, okay, now we've discovered these really wonderful things. We know we've discovered flowers on trees. But how do they get to be flowers? I mean, what's the life cycle of a flower? What's in this little dark patch here? Can we study the insects that are pollinating these things? How do the stamens look like? What do the pistils look like? Oh boy, I can't really discover that with this size telescope. The JCMT had a mirror that was 15 meters in diameter for a long time. It was the largest submillimeter telescope in the world. But at the highest frequencies that you can use the JCMT, you could only get down to about 7 arcsecond resolution. And your eye, I think, well, it's better than your eye, but not much. If we want to study, for instance, those nearby star-forming regions, and we want to look at these newly formed stars and see how the Earth was being formed, or Jupiter is being formed inside these things, well, we need something about 1,000 times bigger than the JCMT. It's hard to build a telescope 1,000 times bigger than the JCMT. It's ridiculously difficult. But there's a trick that was discovered by Anthony Hewish. Was that who it was? A British astronomer realized that you don't need to have a full aperture. you can get away with just having little pieces of that aperture. You don't need the whole thing. You can throw away the stuff in between. You can have pieces of this whole huge aperture, and it will still work the same as if you had one humongous telescope. Not quite the same. I mean, you are still missing the information, you're still missing some information, but you can recreate a pretty good image. So instead of having one telescope 15 meters in diameter, let's have a bunch of telescopes scattered across a plane 16 kilometers in diameter. That's where we get ALMA from. And that was the idea behind building the ALMA Observatory. The Atacama Large Millimeter Submillimeter Array. Atacama is the name of the plateau, in northern Chile. And ALMA, by the way, is also the Spanish word for soul. So I think I just love that. So what is ALMA? Well, needless to say, building a huge telescope, a huge array like ALMA is going to be pretty darn expensive, about $1.5 billion. No one country really can afford to do that. And so Europe, through the European Southern Observatory, which is a consortium of a bunch of countries in Europe, plus East Asia, which is made up of Japan, Taiwan, and now Korea, South Korea. In collaboration with Chile, they built this array of 66 antennas scattered across the plane 16 kilometers in diameter. It's at a site 5,000 meters in elevation. What's the air pressure? It's about a little over 50% of sea level. It's really hard to work up there. That's the problem. Sorry. There, that should stop. Okay. But you don't have to have them only scattered across that large area. You could also have them all grouped together into a compact configuration. This is the ALMA at probably its most compact. You can see there are 50 of these 12-meter diameter antennas. Then there are, is it 12? Yeah, there are 12 of these little tiny antennas. Oh, there they are, right over there. 7-meter diameter antennas. And then there are 4 more 12-meter antennas which don't form part of the interferometer. They're used just for mapping the big scale stuff. But you can have them all crunched together in an area of about 200 meters in diameter. Or you can scatter them across the plane so that as you're up at the summit, you look around and you can see, oh, there's one, there's one, there's one, there's one, there's one. And all working together as if they were one ginormous telescope. To move them from one pad to another, there is this transporter. This one's name is Lore. The other one is Otto. You can see that this is where the driver sits. I got to sit in one, which is kind of fun. But this, it has, oh dear, how many wheels? Something like 32 wheels, all independently driven. It actually moves pretty fast, but this transporter literally backs up to an antenna. Then there's this little ramp. It pulls the antenna up onto the ramp. You can plug the antenna and all the instruments into the truck, and then it takes off and moves from one place to another. Or if there are problems, it will actually take the whole antenna and drive it down to the support facility, which is at a much lower elevation. Here is at the control. No, this is at the summit. This is my one and only time at the summit. They don't let me go up to the summit anymore because, well, I'm getting old. But this was way back when there were only a few antennas. But people don't, very few people go up to work at the summit. Only a very small group of people is up at the summit at any one time. Most of the time we are down here at the support facility, which is at about 2,800 meters elevation. Still pretty high, but it's livable. There's the control room over here, some labs and workshops over here. The new residence is right around, is it? No, the new residency is right down here. There's a new sports facility going in here. The swimming pool in the support, pardon me, in the residencia. That may sound frivolous, but the people who do the work here, the engineers, the support people, the telescope operators, the computing people, and the cleaning staff and everything, they all live here for about 1 week. For 1 week, then they go home for a week, then they're back for a week. So they spend half of their lives here. So if there's a little, a little recreation, little swimming pool and stuff, it's not such a bad, not too much to ask for those who have to spend a lot of time. I am down there maybe 2 or 3 weeks a year, and it's an amazing place to be. There's a control building right there, and because it's a consortium of so many countries, they have the flags up, but of course they're only up there when there are VIPs. Here's the control room with this bizarre-looking guy sitting there, pretending to work. Actually, I was working. When I go down there, I'm one of the astronomers on duty. They observe 24 hours a day, except when it's down for engineering and tests and things like that. So there are 3 shifts of astronomers on duty, deciding what to observe, what to do next, checking data quality, and all sorts of stuff. So there's a lot of stuff to do over the course of a shift. And there are 2 or 3 telescope operators who only look after the telescope to make sure that everything is running fine. Yeah, it's a big operation. But there are all sorts of residents, not just people. Here are a couple of residents. And in the area, it's all sorts of interesting wildlife. This is possibly one of the driest places on Earth. When you fly before going up to the observatory, you fly into the city of Calama, which is sort of an oasis with a big copper mine right outside of it. And then you drive, it's about an hour-and-a-half drive from there to the observatory. You pass through areas where you drive for half an hour and you might see a blade of grass, but nothing else. It is extremely dry. It's had maybe rain once every decade. It gets a little wetter as you go higher. And so by the time you get up to about 4,000 meters or so, that's when it starts looking like this. But most of this is watered by fog, the occasional fog. But there are all kinds of interesting creatures. These are all pictures that I've taken, by the way. Andean condor, the Andean fox. This guy looks like a rabbit, but it's a vicuña. No, pardon me, vizcacha. It's a member of the chinchilla family. Llamas, or actually vicuña, and my wife loves the flamingos. When I have to go down for a couple of weeks, then I get a week on, a week off, another week on the telescope. And when I get the week off, my wife flies down. We spend it up in the desert and hiking around in the desert. It's wonderful out there. It's a really amazing place. Oh, another vizcacha. I make a point of going hiking when I'm up there. And there's one particular canyon that if I hike down into, every time that I've been there, I've found these guys, these cachas. And And so I show these pictures to the telescope operators and so on, and they keep telling me, oh, I've been here for years, I've never seen one. Because I go looking, I get myself into trouble, but that's hey. There are also salt lakes, very high elevation. This one's Sala de Agua de Agua Caliente. It's up at about 4,800 meters or so, 4,600 meters. It's very high elevation, and that's where you find a lot of flamingos as well. And they have mountains made of salt. This is the Valle de la Luna, the Valley of the Moon. And it's also very volcanically active. Here's the geyser up at Aperture. It's the second largest geyser field next to the Yellowstone. Oops. And yes, there are active volcanoes. And here is Lascar, which is about 40 kilometers south of the support facility. I have never seen it active like this, fortunately. There are plans for what happens if there is a big eruption. This one is not big enough to bother evacuating, but if it's big enough, then they have buses set up to take everybody away. But it's about 40 kilometers away, and I've seen it steaming quite often. Have you ever seen it? Have you ever seen it erupt?
I've never seen it erupt and just seen it.
And as I was saying, I like to go hiking and use one of these canyons that are fun to try and find a way in and out. And at the bottom of them, you sometimes find those little biscachos. They're so cute. Okay. And yes, this is the lonely cactus. You can see the support facility in the background here. So, ALMA, what has it been used to discover? Well, I mentioned the studying star-forming regions. JCMT, studying the regions that are directly around these young stars that are in the process of being born. You see nothing, you just see a single dot, a single blob. Well, JCMT, the ALMA on the other hand, is 1,000 times bigger. So it can see things 1,000 times smaller. And here we are looking at a few stars that are in the process of forming. As they start off as a cloud of gas and dust, gravity starts to causes them to start to contract. And as they contract, if they had any angular momentum at all, as they contract, they start spinning faster and faster until finally it's spinning so fast that it can't move inward, it can only move downward, and so it collapses into a sort of a pancake shape. In the middle is the star. You don't see the star in any of these pictures. But what you are seeing is that pancake around the newly formed star. This is HL Tauri in the constellation Taurus. And these pictures, when they first came out just a few years ago, they literally caused they caused my jaw to hit the floor. I had to pick it up and put it back. It was, I got a bruise. It was just so mind-bogglingly beautiful. Why? Because we really didn't expect it. What these images are showing that in these very young star-forming regions, we are already finding planets being formed. These dark circles are caused by planets or planetesimals inside these gaps, sweeping up material, pushing it into the planet, pushing it out away from the planet to form these concentric rings. Here's another nearby star-forming microscopium. This one is almost completely flat on, so they look like circles. Looking into the middle, this splotch may be the star itself, or it may be a disk right in the middle, right around the star. But even there, we have these gaps at all different distances. Here's one that looks like a galaxy. Get spiral arms, probably from large planets in orbit around the star. Here's another one that looks like, well, it looks like a bright blob in one of these spiral arms. Probably is forming a giant planet, or maybe a small star. And this is what this is an artist rendition of what one of these things may look like from close up. Again, in the submillimeter, we're not picking up enough of the light from the star to see this. This would be an optical image. But we get these planetesimals forming and eventually forming a small planet. The planet starts sweeping up the dust and gas and forming these gaps. And we weren't just lucky. We've now been able to do surveys of a lot of different star-forming regions, a lot of different newly formed stars, and it seems pretty common to find these rings and gaps. So they have changed our ideas of how planets are forming. They formed a lot earlier than we expected. Let's skip that. We've also mapped galaxies with ALMA in extraordinary detail. We now have maps of other galaxies that are at least as good as many maps that we had ever of our own galaxy, to be able to study how stars and how galaxies form stars in very large, over the scale of the entire galaxy. But these images are just so gorgeous. I just love them. And of course, one thing that you are most interested in for tonight, I think. Does anyone know this region?
Yes, Markarian chain?
No, well, I'm not sure. Is the Markarian chain in what cluster is the Markarian chain in?
Virgo.
Aha, yes, it is.
That's right. I think
Yes.
see the eyes in
Okay. This is an extremely large galaxy known as M87. Well, before I go on with, you probably would know. What size of a telescope do you need to be able to see visibly the jet at the center of M87? Is it an amateur-sized telescope?
25 inch.
25 inch? Well, how many people here has a 25? You have a 20. I'd love to see it sometime. M87 is a giant elliptical galaxy. It is the largest galaxy in the Virgo cluster and one of the largest galaxies that we know of. When you look at it carefully with a 25-inch telescope or bigger, you see this stripe coming out from the middle of the galaxy. Take a little closer look at that. This is a jet that is traveling at close to the speed of light. It's about 4,500, almost 5,000 light years across. It's a jet of gas that is shooting out at virtually the speed of light. There's something really interesting going on in the middle of this galaxy. We have been able to measure the velocities of stars in the neighborhood of this thing, but right in the middle of this galaxy there is something that we cannot see that is about 6.5 billion times the mass of the sun. Well, there's only one thing that we know of that could possibly be that big, and that's that could be that massive and not be visible, and that is, it has to be a black hole. There has to be a black hole in the center of the galaxy. And we have since learned that pretty well all galaxies have a black hole, a giant black hole in the center of it. But this is one of the biggest. Well, that's great. How do we study that thing? You know what a black hole is. A black hole is something which is so dense that light can't escape from it. The the escape velocity from a black hole is greater than the speed of light. Like, escape velocity from the Earth. If I go outside and if I were Superman, I could jump at 7.5 miles a second. I would be able to jump up and I would never fall down again. So the escape velocity from the Earth is about 7.5 miles a second. The escape velocity from the black hole is greater than the speed of light. Therefore, light cannot escape. Nothing can escape. Well, the point of no return, that is, inside this thing, at this distance, which we call the event horizon, inside the event horizon of a black hole, the speed of the escape velocity is greater than the speed of light. So anything inside this event horizon is lost from this universe forever. Anything outside could potentially escape. And so that point of no return is called the event horizon. How big is this event horizon? Well, it turns out it's about 1,000 times smaller than anything we can detect with ALMA, despite the fact that ALMA is this big telescope. By coincidence, we have a black hole in the center of our own galaxy. And it's about 1,000 times closer than this one, but it's also about 1,000 times smaller. So by amazing coincidence, an angular size in the sky, they're about the same size. Well, okay. Well, what do we need to be able to actually take a picture of a black hole in the middle of this galaxy? Well, we can't use an optical telescope. For one thing, any stuff around the black hole is completely obscured because there's a lot of dust and gas around it. It may be very hot, but it's just completely obscures the black hole itself. Infrared telescope, same thing. An infrared telescope can detect these stars that are traveling around the black hole so fast. It's actually quite neat. If you've ever seen the image of the stars around the black hole in our own galaxy, they've been able to map them long enough to get, at least most of tracks, and then if they push them forward, it's really quite neat to watch these stars, real images, as the stars travel around the black hole. Literally they're going in very slowly, and then suddenly, boom! Look it up. Well, okay. So infrared telescope, yeah, same problem. It's too much gas and dust. Well, we could try using a millimeter or a submillimeter telescope, but the problem is that it's 1,000 times smaller than ALMA is able to. Well, okay. We've already found out if we want to see things 1,000 times smaller, we just make it 1,000 times bigger. So instead of 15 kilometers, let's make it 15,000 kilometers. Whoa, how the heck do we do that? Oh, this is what we think would look like in the center of this galaxy, with a supermassive black hole somewhere in there. That dark patch would be the event horizon, material spiraling in and interacting with the hot gas, and then some of it getting shot out at nearly the speed of light in both directions. The one moving toward us, because of relativistic enhancement, looks much brighter than the jet going in the other direction. We want a telescope that is 1,000 times bigger than ALMA. Well, how do we do that? Well, it just so happens, it's quite by design, that there are a bunch of telescopes scattered around the entire globe of the Earth. In Hawaii, in Chile, ALMA, at the South Pole even. There's one in Mexico, one in Arizona. There's one being built now, or they're just coming into operation in Greenland. One in France, one in Spain. A group of astronomers, led by a fellow named Schieven, this thought that this was about 15, maybe 20, it was at least 15 years ago. They decided that what they wanted to do was to try and join these telescopes together to mimic a telescope the size of the Earth. Now, at the time, there were really only a handful of telescopes that they could use. There was JCMT, there was the Caltech 7mm Observatory, which has since closed. There was one observatory in Kitt Peak. There was one in Spain. That was about it. But nevertheless, they started experiments. How on earth how do you actually combine the signals? With a telescope like ALMA, all of the telescopes are physically connected by cables. The signals come from the different antennas. They're fed into the computer. They apply delays. They do interference, and then out comes the data that they use to create images. Well, they're not going to lay a cable that far apart. So they came up with a plan, which was pioneered in Canada, by the way, something called very long baseline interferometry. If you have two telescopes separated by thousands of kilometers, and you have an extremely good clock, then when you detect these radio waves, you can actually time when these waves come in. You get an actual time. You can measure each wave as it comes in. And you record those waves with the timing onto a magnetic tape, and then you take the magnetic tape or whatever kind of medium, you bring that to a central facility, and you then use a computer to combine them. It was pioneered in Canada between the Algonquin Radio Observatory in northern Ontario and the Dominion Radio Astrophysical Observatory in Penticton. That was the first place in the world where they did that. They thought that they could use those techniques with submillimeter telescopes. Of course, it's a lot more difficult because the waves are a lot smaller. They come in much more frequently. You need a much finer, much better clock. And you need a really fast data handling. So they started the experiment. I was at JCMT when they started the experiment. I was pestering Shep for that they actually got some results. And I started pestering him, and I said, "Can you write a newsletter article for me?" I was the editor of the JCMT newsletter at that time. And he said, "Oh, okay." And he wrote me an article, and I read the article, and I said, "Oh, I can't publish this. This is too exciting. I can't publish it because it's too exciting. Because you're going to publish in Nature, and they won't like it if you put out they don't like press releases or any kind of publicity before it comes out in Nature." So he said, "Oh, thank you for not publishing it." But I still wish I could, because it was a really interesting result, even that, and that was just using 2 or 3 antennas. Now we come to ALMA. These telescopes, well, JCMT is 15 meters. That one's 30 meters. That one is. I don't know what that one is, but they're 10, 12, 6 meters in diameter. They're just little things. ALMA is 66 antennas. So this group, the Event Horizon Telescope group, thought, we have to have ALMA. We've got to have ALMA. We've got to be part of it. Plus, we need other telescopes. So they got involved. They got the South Pole Telescope involved. They got the Large Millimeter Telescope in Mexico. Another group is building this telescope up in Greenland. They approached the ALMA board with our esteemed colleague up in the up there, saying, "We need to do this," and they all said, "Yeah, not yet. We're still building the stupid thing." Finally, about 2 years ago, two or 3 years ago, they finally got the go-ahead. Okay, you can include ALMA difference in making this image. Why? I told you I had very, very, very indirect involvement in this. The indirect is, I was at the JCMT when they were doing their first experiments, and B, I happened to be at the ALMA Observatory as one of the astronomers on duty during the run where they are taking data of M87 and the black hole at the center of our own galaxy. The only two black hole candidates that they could actually do something with. Which sounds really exciting, except that every time the weather got good, the guy from the black hole, the Event Horizon team would come over and talk to me and say, the weather's good, go away, leave us alone, we're going to take over the telescopes. I can't leave. I can't just go hiking, because they may turn the telescope back again. I need to be there. So I have to sit in the corner and do nothing. So it was really rather dull. But it was still kind of cool knowing that that's what they were doing. And he was so excited about how the data were coming in. But of course, it took them 2 years to analyze the data before they finally released it in April of last year. But you can't just throw out a picture and say, here it is. What is it? They needed to know what they were expecting to see. They won't get a picture that looks like this, obviously, because this is an artist's rendition. What would they see? Well, part of the modeling is, how does light behave near a black hole? Gravity can bend light. And around a black hole, it bends light so much that inside a black hole, the light is bent completely round and goes inward. It can't go outward. But light which is near the edge of the event horizon can be bent extremely much. Pretend we're way out here somewhere, looking in this way. These things are, this is a ray diagram. This is basically the direction of that light travels. So stuff that is behind the event horizon, if the light happens to travel in sort of almost any direction except straight out this way, all of that light will be bent toward us way over here. Stuff on the front side, well, it doesn't get bent quite the same way, but it also is redshifted because of the intensity of the black hole. So you really don't see much stuff coming from the front of the black hole. What you should expect to see is something like this. This dark area here would be the shadow of the event horizon, and this bright ring of material is the stuff behind the event horizon. So you're not looking at stuff in front of it, you're looking at all the stuff that's behind it. Well, that's what they expected to see, and well, I don't need to hide this from you. You've seen this. This is what they came up with, and in fact, this is extraordinarily similar to that. I had a lot of people asking me, well, what's the big deal? Can't you make it a little bit sharper? Realize that the pixel size, this is only a few pixels across. The event horizon itself, somewhere in here, was only a couple of pixels across. And just for scale, this is about the size of the solar system. The black hole itself, the event horizon itself, is slightly larger than the size of our own solar system. It's about 120 astronomical units across. So the black hole itself, the event horizon itself, is somewhere in here, What we're seeing is the shadow of the event horizon, and all this stuff is material behind the event horizon, the light of which has been bent around it and is now shining toward us. It looks brighter along one edge because this material is in orbit around the sun, and it's moving at really high velocity, nearly the velocity of light. And stuff which is moving toward us at nearly the speed of light is enhanced in intensity. Anything moving away from us at nearly the speed of light is not nearly so much. And so you get a bright ring with a bright edge along one side. That's only one of the really exciting things. There were something like 10, 12 papers that came out of this, that came out all at the same time. Each one of which was exciting. The Event Horizon team itself has won numerous prizes. I wouldn't be at all surprised if it wasn't the case this year, but I wouldn't be at all surprised if within the next year or so that this team got a Nobel Prize, because this is really quite astonishing. This is the first image of a black hole itself. Now, I mentioned this black hole at the center of our own galaxy. They have about the same angular size, and they observed them both around the same time, not at the same time, of course, because one was up and the other was up. But the problem is that the black hole at the center of our own galaxy it's 1,000 times smaller, but it also means that things happen much, much more rapidly. And so it is extremely variable. It changes on very, very short time scales, which makes the interpretation of the data extremely difficult. So I wouldn't be at all surprised if it takes them another couple of years before they can finally give out the results of the black hole around in the center of our own galaxy. Well, hey, I only took 5 minutes. Okay, 5 minutes over isn't quite so terrible. I hope you haven't fallen asleep yet. But this is a really exciting telescope. I know Jim will tell you just how exciting this has been. I have been having a wonderful time helping to support this telescope. I don't do a heck of a lot of research myself anymore, but I really enjoy the support aspect of it. And so I get to support Canadian astronomers, make sure that they get to use the telescope and they make good use of it. I go out and help with operations and helping with scheduling and all kinds of interesting stuff. So it's been a blast. And I hope you've enjoyed this little slice of the submillimeter universe.
What a wonderful time to be around, eh? Just doing this thing. And you say that it's maybe 4 years ago it's been in operation. So
yeah,
it's got a big, huge future ahead. So exciting times ahead. I'm sure there are plenty of questions here.
Under maximum width, 16 columns, what's the resolution of the ALMA and arc seconds?
Depends on the frequency, but I think it was 7 milliarc seconds. I think that was it. Yeah. For the Event Horizon telescope, it was about 7 million. And it could get better because once they start. 7 milliarc seconds was the Event Horizon telescope. Ask me later, I'll check it. Or check the ALMA Observatory site. I should have brought some of the ALMA primers, because it all says that in there. I edit the ALMA primer, which is a great introduction to it. Sorry.
Mandy?
What's the process like of looking at telescope? Is it, you review individually case by case, like,
Oh.
or do certain countries get a priority for the other country?
If you are from a partner country, then you are put in the pool for that partner country. But that's only after all the proposals are reviewed. Once a year, and it's usually the middle of April, there is a call for proposals. Actually, the call for proposals comes out in March, the deadline is in April. And you have to write a proposal to say, what is the science that you're interested in? What observations do you need? What will you get out of it? And then the proposal itself calculates, well, to do this you will need X amount of time. So once a year those proposals go into a committee. They review those proposals. The last 3 periods there have been 17 to 1800 proposals. And they're realizing they can't sustain that, so they're going to a new model. But at the moment, those proposals, all those 1,800 proposals are reviewed by about 150 people who decide what is the most exciting one? What are the most exciting ones? Which ones will have the best potential for doing really good science? And then they're ranked according to that. The ones at the very top, the very few at the very top are given A ranking. If necessary, they can stay on the telescope for 2 years. Then there's the next group, which is the B ranking. They will probably get the amount of time that they ask. Then there's a C ranking, which is sort of filler, just in case they run out of other projects to do. But at the moment, it's 1 out of 5 that gets any time on the telescope. So it is really heavily oversubscribed.
So there are a bunch of astronomers out there that are probably just waiting.
Oh yeah, who apply year after year and have not had time yet. It gets really quite discouraging. But those people who do get time and do get their observations, everybody is just absolutely ecstatic over the quality of the data. We do a heck of a lot of work behind the scenes to make sure that the telescope data are really good. And it used to be the old days of the VLA, for instance, in New Mexico, that you had to be had to be a black belt in radio interferometry to be able to reduce your data, let alone interpret it. But now they are making it so that pretty well all astronomers with basic understanding of astrophysics don't have to go through the learning how to reduce their data. It's pretty well provided for them.
Nathan, you had a question?
No, well, I was going to ask what was the angular resolution of the Event Horizon Telescope, but
I gotta look that up again. I'm sorry, but you go on Wikipedia, you'll find it right there. Or look up the Event Horizon Telescope. They have a really good outreach. And ALMAobservatory.org has a lot of really cool photos on it. And ALMAscience.org is the science one, and it will tell you everything more than you could possibly want to know. And if you're really interested, look up the ALMA primer, because that's one thing that we produce here in Victoria. I should have brought a copy. Yes?
Just a technical thing. What fraction of the time are all of the dishes working, or what fraction of the dishes are working at any one time? I guess
There's what's called there's minimum number or a blocker number. There need to be at least 43 antennas working at any one time.
Oh, okay.
That's for the main array. There are 50 antennas in the main array, and 43 of those have to be working. And there are 12 antennas in this compact array, and at least 9 of them have to be working.
Do you run into periods at all where you have less than that? And you have
Yeah. For instance, when if there's wind, some of the telescopes are not as robust as the others. And so when there gets to be a fair bit of wind, they have to shut those antennas down, and then you're really at risk for stopping observing. But it's not a big fraction of the time. Daytime is the worst for wind. Wind seems to pick up in the early afternoon and then drops after sunset.
It's interesting because wind is a problem for us too.
Yes, yes. But these things are all out in the open. They're big sails. Chris?
So, is it possible, or would it be possible if there was enough telescopes, because you're really looking for end-to-end, the aperture is effectively the two furthest telescopes of each other, to have two scientists sort of working on two different subsets of telescopes, to split the array in 2 or 3 or whatever?
Yes, you can do that. They don't do it for science, but they do it for engineering. So they need to test an antenna. So they will split off 2 or 3 antennas to work with the one that they're trying to do calibration or whatever, and they'll be doing that separately. That's one thing that the telescope operators take care of that, where the astronomers on duty are just taking care of the science. In principle, it's possible to do that, but generally you don't bother because the image quality goes up as pretty well the square of the number of antennas. So if you divide your antennas by 2, then you're only getting a quarter. So you might as well do one project and then the other.
So another question is on the technical side, actually going back to a single telescope like the one, whatever. I'm trying to picture, so microwave would be right on, sort of halfway between radio and light, and the big
Infrared,
antennas.
I like to think, actually I like to think of it more, not so much as being microwaves, but more very, very far infrared.
Right, so it's close to light. So this is never really, that never occurred to me before. I always pictured these as radio antennas or something like that. But of course the big difference would be that the radio antenna is like a single pixel antenna, and a light telescope is a massive resolution. I'm talking about the actual detector.
But that's only because of the technology.
And
They are working on multi-pixel arrays in the radio, and they have multi-pixel arrays on things like the JCMT, and they keep building more pixels. The scuba instrument, the one that that picture that I showed of the Orion in submillimeter was actually taken in using the Scuba 2 camera, which is it's a bolometer camera, which means it's not looking at spectral features, it's looking at the broad spectrum. It's got a big wide bandwidth. But it has, oh dear, how many pixels does Scuba 2 have?
16,
No, that's Scuba 1. It's about 1,600, I think. It's a lot of pixels.
So that was my question. So you can actually get arrays of
Yeah.
in the millimeter range, these type of, and you could have it as an array similar to the
But you can also put arrays on. They're actually making studies of whether you can put arrays on ALMA. The problem is that there's only so much space in these cans. ALMA has receivers that cover the complete spectrum from about 80 gigahertz up to about a terahertz, with a few gaps, just because there are gaps in the window that let radio waves, let these waves come through. So it has a complete spectrum. You'd have to throw away a bunch of those in order to have enough space for an array in there.
And are they super cooled, those things, or cooled?
Yeah, they're cooled.
Like
Liquid helium? Yeah,
Oh, gee.
it's cold, very cold. Only a few degrees above absolute zero. What was I going to say? Oh, by the way, an aperture synthesis telescope works, though, even though it's only looking at one spot. it's measuring all the structure that falls within that one spot. And so by combining, by interfering the signals from two antennas, you are getting information about the size, about the structure within that. And so by combining all these pairs of antennas at all different distances, you are getting all the information that you need to turn that one spot into a full image with some limitation. You don't see anything finer than you get from the biggest distance, and you don't see anything coarser than you get from the smallest distance apart. So you have to think in Fourier space.
Okay, any other questions?
I'm coming to coffee too, by the way.
Oh, excellent. Well, I've got some questions to ask you there. As a token of appreciation, we have something that I know you already have, actually. This is a beer mug for Plaskett's Big Dipper, but in the spirit of the ALMA project and the New Horizons, more of these working together makes a merrier town.